Well, welcome everyone, and I think we've got people from Vicnor. I didn't know you were in Turkey, so welcome, and hopefully your day went well and you have a good evening. See a bunch of other folks from a handful of regulars I've noticed, and I appreciate you coming back again. And so please let me know if the sound is working. It's always kind of unnerving as I get started to know if it's working or not. If, one or two folks could let me know, I'd appreciate it in the chat window. Yeah, I see a couple people are typing, so I think that's working. Sound is good. All right, great. Thank you. And Colleen, it's good. I appreciate that because I know you've had some trouble in the past, so I'm glad it's working today. Well, today I wanted to talk just a little bit about a couple of cases of using data, using statistics, um, in just as a nudge for everybody on the line and those viewing the recordings to look for and use data, use the statistics that we have available for us. It's one of the key elements of being, for me anyway, it's a key element of being a reliability engineer is the making use of data. I've also found it to be very, very useful and powerful. And I had a manager one time that said you should speak with data, and being able to plot it and draw conclusions and make convincing arguments is a big part of being in my mind, being a reliability professional. So that's what I wanted to talk about a little bit today. And I'm also very interested in how you make use of reliability statistics and how you use statistics in general. So we're going to have the chat window open throughout the presentation. And so please chime in with questions. I'll keep an eye on it and answer any questions as we go. But I also want to hear, what's working for you. If something sparks a similar story in your world, do let me know. That would be great to share that also. All right, so let me pull up the presentation, rearrange things a little bit, but hopefully everything's still working. And I want to mention that for the to see what other webinars are coming up and where the recordings are, it's on Ascendo Reliability, and that's I should probably type in a address for that. It's Ascendo. It's a relatively new site I've added to my website, but the recordings for past webinars are there, a bunch of other information, a couple of ebooks that I've written that are up there, a couple more on the way. But you can find a bunch of information there. And so I'm working on making this a hub for professional development. And let me know what you would like to see there, or what you would like to have available, and we'll see if I can make that happen on that site. So for those that I think we're just about 100 members strong so far. For those that have already appreciate it, but do let me know what you'd be interested in seeing there. All right, now I know that this is early in the morning for some people, and so I've avoided using any uh, integrals and hard math and all the other happy stuff that's there. But I am going to show you a couple of things that should help you get going with statistics. And I don't know about you, but I've done this every now and then where I ask the group, well, I'll ask you, how many of you have had a statistics course? Say an undergraduate or a graduate level data analysis course or a statistics course. And yeah, a bunch of people. And I would imagine almost everybody on the call and everybody that probably that you work with, engineers and managers and technicians, all kinds of people have had a statistics course. Yeah, taught yourself 20 years ago. That's the way to do it, George. Uh, how many of you enjoyed it? Now, be honest, how many of you have enjoyed statistics? And I would say there's a few, because that's kind of the nature of our work in reliability engineering is we we're the type of people that tend to enjoy the statistics, so it's kind of a self-selected group. Keep in mind, though, that the people we work with generally don't answer positively to enjoying it, right? So part of what we need to do is make reliability statistics and statistics in general, make it accessible for other people, help them get the information they need in a meaningful way. And so that's a big part of what we do. Now, as you know, everything varies. When we make a product and we buy parts, the individual capacitors and the molded components all have slightly different dimensions. Um, our customers all operate our equipment in slightly different ways. Our production lines is creates products that are no two are alike. Um, Sometimes you have to get pretty darn close to it to see the differences, but it's a matter of that this process that we use to create products or to create services has variation with it. Some of it's human generated, some of it's machine generated, some of it's material science, material variation, and so on. But the notion is that a designer is unfortunately unable to say, I want this to be 25 millimeters in length, and that every single one that is produced will be exactly 25 millimeters. Now, they put a lot of work into what's the right dimension, and then then what's the allowable amount of variation, and we call it a tolerance or tolerance limit. But that's kind of the start. Now it's a matter of can we actually achieve that? What varies or doesn't vary that makes a difference. Now in reliability, we often think of it not just as a tolerance on a drawing, but time to failure, time to how long does something last before it has a failure. And that time measurement becomes the variable that we're interested in. So if we made three different cactuses, say, what's the expected lifetime of each one of these things? And then as we measure different species of cactus, how long do they last? And we could use statistics then to describe that behavior, that notion. Yeah. And George, I just saw your note is that it's, you know, math understanding and you know, I don't know where that comes from. I think many of the folks we deal with and many of the teams we work with are are using math in a day-to-day basis already. I think some of it is our own doing, though, is that we don't present it in a meaningful way. We don't show information in a convincing way. And this plot here is, I just threw up a couple of curves, the stress strength curve, and we use this concept regularly, and so do mechanical engineers. I believe they're taught this in school. And that probability of failure, that overlap part, is the integral of if my stress is large enough and the strength is small enough, then it'll cause a failure. It's one way things fail is they get overstressed for their strength and they fail. Now keep in mind that both the stress and the strength move and change. So as materials degrade, the strength gets weaker. As customers use our products more aggressively, the stress gets higher. Um, Also, the variation of these things. Different customers would have different stress profiles, and different kinds of products, batch by batch, may have very different strength profiles. But the all too often is what we see is somebody will use just the average strength and the average stress. And that notion of only the pictures show. Okay, I'm seeing, Leonard, you're just getting one piece of this. Is everybody else on the slides? You should be able to see the stress strength piece of it. Got it. Oh, good. Okay. So Leonard, maybe I'm not sure if you have a sync button at the bottom right-hand side, but it should be there. Um, but okay, well, I'll drive on. I'm not really sure. Maybe um, log out and log back in, but I'm not sure, Leonard, what the deal is there. Another source of variation, I guess. But the idea is that this is the very, very basic part of what I mean by using statistics is if we're going to do say a environmental test just for temperature, we might pick say 40 or 50 degrees C as the high end of our temperature. But where does that actually land on the stress curve? Is 40 degrees in different units here, obviously, but is 40 degrees here or is 40 degrees here? And where's the rest of the distribution? Where's the spread of this data really show up? Nominal might be at 20 degrees C or 25 degrees C, and 40 is near the upper tail of this. So we're starting to get a range of values there. But I'm going to show an example in a few minutes here that talks about, there is data available to calculate that. And then as we do strength calculations, it's not merely enough just to say, hey, it worked for 10 hours at 40 degrees C. If the prototype's actually working, that'd be great. But the idea is that the multiple units will have different strengths. So part of our work is to understand what's that variation, what's the range of values of strengths that apply. Of course, the best way to do this is test them all, test them to failure, and we'll find out what this lower tail is, this blue line. Unfortunately, we wouldn't be able to sell anything. So a lot of times we do just basic statistics, a sample, to find out what's the spread of ranges. And in some cases, people will actually create products that are a little bit weaker and a little bit stronger as an idea to get the range of values into testing to see where this curve really stands. There's a lot to these curves, and trying to just describe them is often a challenge for us. So I want to use that as just an example to get us started thinking about it. Now, environmental testing, we do a lot of, and there's a lot of, we can leverage that oftentimes into time to failure if we understand the failure mechanisms and we have enough samples to make a meaningful estimate of the values. What I'm going to say is that testing to a specific value, say just 40 degrees or 45 degrees, or a specification of some level of humidity, say, plus some tolerance, some margin over that, doesn't give us as much information. It gives us pass-fail information, but we got a lot richer information if we test to failure. Now, it's more expensive, yet we get orders of magnitude more information. So even in environmental testing is calculate the statistics of, well, what does this test mean? If I test 5 samples and I test to pass, I'll probably have a very low confidence that it will last very long if I look at it that way. If my environmental testing is to simulate an aging of a product, say for a year, well, what does the result really tell me? And so we can use binomial and chi-squared and other distribution techniques to calculate, well, what's the defect rate that I would have seen or could have detected if I have no failures, and how sensitive is this test for? So there's plenty of tools out there to help us sort that kind of thing out, but ideally, whenever possible, is run it out to failure. See where those margins really are and see what kind of information you can get. So as we look through our programs and we're working with our teams, it's look for where you can get better data. So test to pass is some information, test to failure is even better. And that's my main point on this particular slide. So I mentioned weather data, and I'll bring it back up as we get closer to the end. Is there's a link in the links tab. I don't believe I have that window open at the moment. Well, I think I can open that actually. Let me see if I can do that. There's the NOAA, National Oceanic and Atmospheric Agency, I think is what they're called, has a part of their website that has, let's see where it's links, web links. Yeah, here we go. Let me drop this across here for a moment. So the weather data in this links tab will take you to the website, and it has some other four-letter acronym, but it's part of the NOAA site that you can go in and search for or find weather data by different weather stations all over the world. And so what's on the screen right now, it was I did it for a client of mine a few years ago where they were going to put products in California, in a high desert area. And what they wanted was, well, what's the 90th percentile range of values that we're going to get? How hot is the absolute maximum, but also what's the typical hot day like? And what's the average day? And how cold can it get? What's the range of values we would expect? And so what we did is I gathered, I had 20 years of weather data from, I think, 30 different weather stations. So this plot is, I think, 65,000 points, and the weather is recorded, or the temperature is recorded every hour. So it's a lot of data. I just made a quick histogram of it, and we could fit a normal curve to this. It's not quite normal, but we could just use the histogram itself. And even in Excel, I can say, well, what's the percentile, the 10th percentile or the 90th percentile? And we came up with the values we were looking for. Basically, it's as we would expect. It ranges from about 0 to 40 degrees C, with the nominal was a little bit less than 20 degrees C, which surprised me. I guess I'm always thinking of office environments at 20, 25 C. But here I had the real data. This is the stress curve. This is the actual values. And so we could use it in Monte Carlo. We could use it for test planning. We could say, well, what ranges are we actually going to evaluate and test for, and so on. Now, we also used the same technique to look for their second place they were going to put this product was in Ontario, Canada. And it was a slightly different weather data histogram. It was a little bit cooler. It got much colder in Ontario than it did in Southern California. It did get as hot, and it had more humidity. So the weather data helped me to figure out, especially for products that are going to specific locations, it gave me the hard evidence of what the stress curve was. So I believe the link underneath the weather data will give you access to all of this information, and it's free. It takes a little bit of work to download it and put it all together, but I'm certain you could sort it out. So Sherry, are you in Ontario or in Canada? Minus 18? Oh my, a little off of this curve. See, that's part of why I like being in California. This is a more typical pattern for us is in this range. And where I live near the coast, we rarely, if ever, see above 30, 35 C. So enjoy the Great White North there. So the question for you is, so I'm going to ask everybody, do you use weather data or data you gather from your instruments to modify your environmental test? Do you use the statistics to determine your stresses? No. Okay. A few other folks are typing here. Sometimes. Yeah. Sometimes it really is. Sometimes it's not easy to get the data, and especially in low volume type things, it may be very difficult. Um, Geez, 20 some years ago, I used to use data loggers with a bunch of thermocouples and measure sensors hanging off of it, just to stick it in a location and try it. Um, a completely different example is, I may have told this story before, but I was working with a game controller team, and had, I don't know, 25 or so buttons on this little controller device. And I asked the question, figuring these guys, the mechanical engineers designing it, could answer it, was, well, how often does a gamer push the A button? How often does he push the trigger? How often do they push, the directional buttons? And they had no idea. And so the testing was to 1 million button pushes. And so they had all these little mechanical devices set up, mnemonic devices, just pushing buttons day in and day out. It'd take weeks and weeks and weeks to run the test. And it wasn't terribly useful. It was expensive and a long duration, but not telling us much. Uh, so it turns out that the same group also brought in people to play test different games and different equipment almost every day. And so I found a little device that would record all of the signals from the game controller to the console. And so every button push was recorded. And with a little bit of work, we sorted out for an hour of playing a particular game how many times buttons were pushed. And they had people who were brand new to gaming, so very low skill basically, and were learning how to use the system, to professionals. There was actually people they brought in that would go to gaming conventions and conferences and so on as a professional and compete, and looking at how they use their systems. And it was amazing. They weren't as fast or faster than the fastest people, uh, but I guess they were more accurate at when they used their systems. But we were able to count all of the button pushes within a typical hour for a whole range of different people, and again made that stress curve. And it was nowhere near 1 million button pushes. So those tests that we did added a lot of margin. But without that data, without a little bit of work to go figure out how to measure it, we were pretty blind. We didn't know whether the testing was good enough or overkill. Now we knew it was way more than it needed to be for many of the buttons. There's some like the Wi-Fi linking button. It gets pushed maybe once or maybe 10 times in its lifetime, but they were testing it to 1 million cycles. So once we came up with all this data, then we said, let's adjust our testing to be more meaningful. And then we did a bunch of other things. But the same with temperature or humidity or rainfall or vibration or whatever. Yeah, it might take some investment of time and some censoring maybe to go out and measure that stuff. But then it allows you to really make good decisions about how you set up and run your testing and how you set up and evaluate the results. So if we get a failure at the max temperature and it only affects less than 0.5% of our population, well, what happens when I back off to 90 percentile, which is it would affect 10% of our people if it failed there. What are the results at that point? Let's start making those kinds of uh, informed decisions using the data that we have to collect. So here's an example uh, looking at escalators. And these escalators were in a public transit facilities. So think of going down to the subway kind of escalators. And some of them were exposed to the street and not covered at all, so they saw rain and all the environmental conditions. And some of them were inside the system, so under roof and more like not perfectly protected, but they were sheltered basically. And so the system used these kinds of metrics. They put them up on the walls in the different groups and reported it to management. And they basically just counted the hours of when it was supposed to be running. I think stations were typically open about 20 hours a day, 18 to 20 hours per day. And they just counted how many hours it was actually running versus how many it was supposed to run. And everybody knew that the street escalators had much harsher conditions, um, exposed to the elements, basically. And so lubrication and all the other features of that system degraded much, much quicker. And they were much, much dirtier systems in general. And they broke down very often. And when they did break down, they failed for a long time in some cases. And they had some escalators out of service for 6 to 12 weeks, waiting for parts and stuff. So other issues they were having. Now the same types of escalators, same industrial grade escalators, but with a roof over them, did much, much better. Now this isn't great to be at, and I think, sorry for being so fuzzy there, but the goal is like, I think 98% availability. which if you're looking at 3 stories of stairs and your escalator is out, it's not a good thing. And so but this is the kind of things they tracked. It was the actual, and they had sensors on all these things, so they knew when it was running versus when it wasn't running, and then monthly they tallied this stuff up. So once again, I went looking for data. Now they had a CMMS system that tracked all of the work orders. So anytime an escalator went down, and this data is for one particular escalator, and time is in hours, and the vertical axis is just the count, how many failures occurred. And so this is over a period of a year for one machine. And I found the data in the work order system. So every time they rolled a technician to a site to go look at it and do some repair of an escalator, they always shut down. The station agent may have heard something weird, or a sensor got tripped, a safety sensor got tripped, or it wouldn't start in the morning. It was very, very common. A technician would go out and look for the cause of the failure and then try to repair it. Now, of course, these things failed at the start of the day, and within an hour then or 2 hours was the rush hour. So there was a huge emphasis of getting it up and running, which I fully suspect is very nothing new for most of us on this call, is that we want our equipment running. But what happened is as I started just plotting this data, this is just every date time when there was a failure, I recorded it as a time when that system went down. Now, this kind of plot, assumes that the repairs are relatively quick. So when you see a blue dot there, it might be down for an hour or so. And that happened most of the time. Not always, but most of the time. You'd have to annotate this for when there was an extended period of downtime, and that did occur with some of the systems. But what became very apparent as I started looking through the data is this sawtooth pattern, where it was moving up and then kind of nothing would happen for a while, and then it would be another series of failures. And this would be in the order of days and weeks that we would get a sequence like this. There's 3 or 4 failures at one spot here. There was, 8 failures in a sequence like that. Another group of, say, 8 or so. And I was reviewing the data, and I'm just the statistician at this point, looking at numbers. I'm not a maintenance technician for escalator. But what it did is it said, why is this pattern happening? Where did this behavior come from? I suspected some ideas as I watched people doing maintenance and went out on these calls. But I sat down with a number of the technicians, and they said, well, when you first go look at an escalator, basically it's not running. The station agent has turned it off and put barricades on it. And so we take a look at the panel that may tell us what happened, and oftentimes it says a sensor was tripped, or maybe it doesn't say anything, it didn't start. The error codes aren't all that descriptive. So the first thing you do is just start it up, see if it runs. And oftentimes, as you probably know the rest of the story, it just ran. And they'd watch it for 20 minutes or so, watch it go through its cycle, and they'd turn it on off a couple times, and they couldn't repeat the failure, and they'd say no trouble found and walk away. So Ray, the vertical axis is the count. So it's, and you might not see it, you might have to open up the screen a little bit, but it's in 10, 20, 30, 40. For some reason, the ReliSoft package put in 3 extra zeros as fractions, but they're just literally just counts. So this is 10. So at this point, at about, looks like 4,500 hours or 4,200 hours, something like that, which is about half a year, about 6 months, it had its 10th failure. So this point here is its 10th failure. And that's number 11. And then this line here is for 20 failures and so on. So sorry for the confusion there with the extra zeros. Never did figure out why it was doing that. But the point is that this was it's providing just a simple graph. That's all it is, a simple plot of the data that allowed us to ask better questions, to take a look at why is it doing this? Why is this happening? So the technician would go out on, say, Monday morning and restart it and run. And then Tuesday morning it failed again. And then Wednesday morning it failed. Wednesday afternoon it failed. Wednesday evening it failed. And each time that a different technician was called to the system and just did the basic troubleshooting and started it again. Until eventually somebody said, there's something wrong here. And they opened it up and looked for debris or oftentimes it was something in those combs at the top of the escalator that slide along the teeth in the steps. And if something gets underneath that, the sensor is very sensitive to that flap moving up. So as say a penny or a nickel or a coin or a screw or something gets jammed in that, any little debris and vibration then makes it much more likely for it to trip the sensor, but it becomes an intermittent failure. And so finally, a technician said, I've been out here 3 times in the last week. What's going on here? And then they would open it up and take things apart and do some cleaning and they had a routine of things that were likely to fail. But when they first went out to it, they know from experience that 2 times out of 3, you restarted and it would just run. But by plotting this data and showing this over and over and over again on all kinds of systems, all these escalators, we changed the maintenance process that on the first call, you take the extra half an hour and you open it up and you clean it. And it got rid of this staircase type approach where it would go multiple intermittent failures and then another set of intermittent failures. And it went to much more just along the curve, more of a random sequence of failures, and significantly reduced the number of trouble calls. And so we had time to do preventative maintenance. So this is statistics. This is just plot the data. And the whole idea is that it allows you to ask better questions. So I'm quite sure many of you have done stuff like this, and I want to encourage you that if you haven't, to do it. Just get it on a graph and see what story it tells you. Oftentimes, just asking the right question is the whole challenge and battle. So I think many of you know my thought on this is, if you're going to do MTBF numbers, I would say, stop that. Just get a plot. I mean, cumulative plot, a time to failure plot, a cumulative distribution plot. There's all kinds of ways to plot data. Even a control chart, a run chart, all those kinds of things. Histograms, all much, much better than just a single number. It gives you much more rich information, plus the ability to query the data, ask, why is this different than that, and so on. So highly encourage you to do that. So in another case, and I'm quite sure many of you have had to deal with field data or had the ability to gather field data. Now let me preface this that I have yet to find a system that had perfect field data, right? Very, very rarely does every customer tell you about a failure or give you meaningful information or send the product back. Sometimes you just throw it away and move on. Sometimes we get garbled information from the system. It might be a warranty repair center, but they don't tell us what actually failed. They shotgun a bunch of parts in there, so it's a lot of no trouble found when we do deeper analysis. Often I see hopefully I won't ask everybody how you do it, but I just see plots of percent return per month or the number of returns per month or the dollar value of returns per month, seen it a variety of different ways. But that's just a count. right? And then some people will divide it by the number of units under warranty, for example. So warranty return rates, kinds of things, and a grand average over the warranty period. Those are okay. It's a start. Let's get a picture of what's going on there, but it's often not very rich. It's not a lot of information in there. So we have time to failure data when we get returns. We just have to sort out when that unit was shipped or put into service if we can get that information. So let's get some better information. Is if we get that time to failure data, that's gold. That's really, really useful stuff if we treat it well. If we take it all together and do a grand average, or we bundle it together by failures per month or different numbers like that, we lose a ton of information. So it's the notion is to start using um, the time to failure data directly. And my favorite, and I suspect many of your favorites, is to use a cumulative distribution function. Now this plot's a little bit busier than I typically like, but the um, x-axis, if and I mentioned it in the start in the chat window, but if you mouse near the top of this window where this chart is, you'll see a menu bar show up, and I believe you get something about here that'll allow you to expand it to full screen if you'd like to. And I believe it's escape, or just click on it again and it'll bring it back down in size. But the horizontal axis, as you know, is the log of time, and here it's in months. And the vertical axis is the proportion failed. So here's 1% failed, 5% failed, 1% failed, 10%. It's also in a log scale, 90% failed. And in this particular graph, this yellow line is the overall system, just all failures. And then we had the data as to what was the primary reason it was returned. This product, it was a medical product of some sort, and it had a solenoid, a sieve device, they call it a subsystem. The plastics was the case, the outer shell of this thing, um, and a compressor. And there was a couple other pieces to this, but they just fell off the chart as being pretty insignificant number of failures. But what we found was that the case parts failed initially and then had a very shallow slope. And I don't know if these are lined up correctly or not. Yeah, I'm not seeing the appropriate data, but it had, usually these things failed on installation. Somebody would drop it, or it would go over a transom or over stairs, and the case would get fractured and be returned. So it had a classic early life failure phenomena, and some units would fail and then get returned pretty quickly. Uh, but as they got moved around from customer site to customer site or within a home, things would break on those cases. And, and eventually, though, the compressor, I think it's the red dots here, uh, which had a very high beta value, if I remember right. It was a 2.2 or thereabouts, and I think there was one item in here that has a little bit higher failure rate, or a rate of change wear out mechanism. So at about 8 months or so, the compressors started to dominate the failures. And as they continued to track this data, it became very true is that the compressor became the dominant failure mechanism. And eventually it was going to change the slope of the overall system as it took over more and more of the failures that were occurring. But what this plot did is it gave us the field data for the next generation or for product improvement is what the priorities were. So at the first month or second month, it was the case, the plastic bits. And the other two parts, the compressor and all the other systems, had very, very low failure rates initially. But it gave us, if you look at this vertical line, it gave us a Pareto of what systems were contributing the most at, say, the second month of service. But if we go out to 12 months, which is in this range, now it's the compressor, and there's the solenoid is kind of a close second. then the case becomes a priority, and then the sieve is still insignificant compared to the other ones. But it gives us a rank ordering or a Pareto at different time slots of what we should work on. So hopefully this isn't anything new, but it's a reinforcement of one way to use our field data. Now, if I just do the Pareto directly of all my failures I've received, say over the last 6 months, I will get some combination of these two Paretos I just outlined and not a clear picture as to what's important when. And realizing that they're very different sets of circumstances for factory escapes and installation, early life phenomena, and versus out towards the 12 months, which was what I think their warranty period was. And so it was taking a look at the available data, sorting it out to the subsystem is the best resolution we had at this point, but it allowed us to then go to the teams and saying, hey, mechanical guys, get the plastic right because it's dominating the failures in this early 6 months or so of the product's performance. But lurking just below the surface out at 8, 10, 12 months and beyond, whereas these two components, the red dots and the black triangles, the solenoid and compressor, were wearing out too fast. So how are we going to shift these things so that they're lower into the right, meaning that it takes longer before failures occur? And it's really one way to communicate it on one slide, very effective, how the product's risk of failure changes with time. And as we created the new product, we started looking at failure mechanisms and life testing to create a similar plot, but for the products that we're designing and developing. And so we use this subsystem kind of plotting to then aggregate it up to the system level and see if we're on target for our goals or not. And it became much, much more useful than using an average or an estimated monthly failure rate or those kinds of numbers. But by looking at the change of failure rate, it became much more visible and much more clear. When I first showed this to the program manager, she said, you know, you explain this and I think I understand it. It makes a lot of sense. But can you summarize this in one number? I said, not really, no. And her concern is that the senior managers wouldn't understand it. I said, well, let's try it. Let's just put it up there. And she explained it in about 2 sentences, and the management team got it. They had no problem whatsoever. Um, Sometimes you have to use brighter colors for more senior managers, but generally they can understand a graphic once they understand what the axes are. So try not to summarize it too much because you often then lose a lot of information if you average it and put it out. I like uh, poking at senior managers and I'm sure you've all seen it is they want charts with red, yellow, green on it. Um, let's narrow down our problems down to 3 issues. You know, what do we got to pay attention to and what's okay? And oftentimes that doesn't tell enough of us the story as to what's really going on. But in that plot, I mean, we're calculating as 1 minus the reliability on that plot and 1 minus e to the negative t eta beta term, but it allows us then to use just a little bit of math, right? Now, I promised in the title that this was going to be, of course, a discussion of using reliability statistics. So I had to have a formula in here. And this is the Weibull formula. Once I get that beta and eta, I'm off to the races. I can do a lot of calculations. I can answer questions about how many are expected to survive through the warranty period, for example, and the finance group needs that. How many spares do I need from 6 months to 1 year of service? I can calculate that with some manipulation with these formulas. So it's something really to keep track of. So let me ask this. I'm getting closer to the end of this thing. I think I have one more sample or one more example. What plots do you use? What graphics do you use? I think I've showed just three of them so far: a histogram, mean cumulative plot, and a cumulative distribution plot. Weibull, Weibull, yeah, Weibull and log. I've used log normal a handful of times for repair times and seemed to fit that very, very well. Okay. Pareto histograms, good, good. You know, they say a photo is worth 1,000 words. I think a well-constructed graph uh, lets you tell lets the data tell the story and lets us all ask better questions. Good, good. Lots of Paretos. Yeah. Hopefully, Larry, you see the idea of this cumulative distribution function with the subsystems under it, and it could be failure mechanisms under it. It has the information that the Pareto lacks is what's the changing rate of failures over time. So that might be another way to look at your data. All right, I get rid of this green arrow that's hanging out there. It's messing up my colors a little bit. All right, so how many of you get the question, so how many samples do I need? And you know people are asking us that because we're doing a little bit of statistics or we're setting up testing. They also tend to cringe when we smile and say, you know, they know we want more samples than they have. Yeah, failure rate trends. Yeah, Ray, those you got to be careful with. It's take a look at what's the changing nature of the different failure mechanisms. That may be another way to look at it. Yeah. So I'm sure you have gotten this question. What's my sample size? You know, I've only had one case where I was working with a solar panel team, and they were one of the issues they had was that the zip ties, the little plastic ties that held the power cables, that as the power was generated by the panel, they would string these cables together in the field to carry off the power that was being generated. And they would use zip ties, these little plastic ties, to connect it to the frame to keep the cables tight and connected. And there are a lot of connectors. So they also used a very inexpensive connector that didn't lock. The idea was that if you held the cables in place, you didn't need a very strong connector. Well, it turned out that the zip ties, these little plastic things, would age through oxygen and would eventually become brittle. And so wind would come up and rattle the solar panel a little bit, and those ties would break, thus separating the cables. And so they'd lose power output. And that was the only case where I was handed literally thousands and thousands of samples to go do life testing to compare different vendors and different formulations of these ties. Most of the time, I get one or two samples. Uh, but this is a formula that I found that I've it's easy to remember, but it's based on the binomial with 0 failures. And so the way to read this thing is if I'm going to test something for one lifetime, say the number of cycles equals 1 year, or the number of car door opening and closing is estimated to be about a year's worth of it, or whatever is your lifetime. If it's just one lifetime, M is 1. If you can run the test for the equivalent of 2 lifetimes, then M would be 2. And sometimes we use this other, like temperature or the Arrhenius equation to compress the time, say that that oxidation factor would be, but somehow come up with what's the equivalent for a lifetime or a fraction of a lifetime, and that becomes this value M. R is the reliability, the probability of successfully surviving the M1 lifetime. And C is our sampling uncertainty, type 1 error. And so the number I remember is if I'm running a test that simulates one lifetime, where there's a lot of assumptions and considerations in that, but let's make that, say we're running a test that simulates a year, and that's one lifetime. If I want to show that we have at least 90% reliability, and 90% will survive 1 year, this R becomes 0.9. And let's say we want to use 90% confidence, that there's a 1 in 10 chance that our sample will not give us a representative answer to the population. Then I'll need 21 and a fraction samples or 22 samples. And they would have to run for that lifetime without failure. And so that's how this formula works. It's a very efficient sample size. Once I have more failures or I run two failures, then there's other formulas this doesn't apply anymore. But if you're sitting in a meeting or looking at a data sheet and a vendor is saying, hey, we ran 77 samples, if you can sort out how that test relates to an expected lifetime, you can very quickly calculate, given a confidence, what the expected failure rate that they were able to demonstrate was, or vice versa. Is it good enough for what you want? So sample size is a big part of what we do. In Salvatore, C is the confidence, so that the type 1 sampling error, meaning that if I take a random sample, say of 4 raspberries, and use that to make a judgment about the population, there is a chance that I'll get nothing but the very sweetest raspberries, and it'll skew the results, and it won't be representative of what the true unknown population is. So that's what C is the type 1 confidence that we see quite often with hypothesis tests and confidence intervals, things like that. So hopefully that helps a little bit. But this is a formula that you can do very quickly and make a quick judgment whether the just because 10 samples passed some test, it might be at 60% confidence, showing that not more than half of them should have failed. It might be a very low power to that test, or ability to find failure mechanisms. But it's a very quick setup where you can compare what's my sample size, the cost of running the test, versus my sampling error, versus what is it showing? What failure rates could they detect, essentially? So if I'm running a test that has, say, 60% confidence, it's not a lot of confidence. The sample is representative, but it makes the sample size lower. But if it only shows that a 10% or more will survive 1 year, it's pretty ineffective at finding defects unless it's affecting every single product, or at least 95% of the products. So yeah, Bandor, the question on, let me answer David's question. No, this doesn't assume an exponential distribution. This, and there's a more general form of this where there's a beta over this m to account for Weibull distribution, the beta parameter, the rate of change. But it doesn't assume a distribution at all. It's basically doing a pass-fail task. So it's really based on a binomial. And it's not the most efficient test. It's not the most clean way to do it, but it's a quick way to check, well, what kind of sample size do I need? So if I'm starting a program, I need to come up with sample sizes. Well, let's put some numbers here. So the R, to your question, Bandor, is start with the goal, and what's the goal of the product, and let's break it down to either this particular failure mechanism we're evaluating or to this particular subsystem, and what's its apportioned goal? How good does it need to be? So if I need this part to be at least, say, 95% reliable for 1 year, this would be 0.95. And what's the risk I'm willing to take? And then I can calculate out how many samples I need. So it's one way to get to those. The other side is you can solve for R, given that somebody ran a test. What confidence are you willing to take? And then you can solve for R. What is that test demonstrating is the minimum reliability of that set of samples? So there's a couple ways to use this thing. But But it's a simple way to get at this idea of, well, how many samples do I need? If you're doing degradation testing, where you can monitor say, the wear of something directly, it's a whole lot more efficient. And 20 samples is a good number to calculate that. And there's other techniques, but this formula is, one, easy to remember, and it balances, well, how good do I need it to be, the R, what sampling confidence do I want to have, and then how many samples do I need? So it allows us to do some trade-offs real quick. And what I found is that if I have a very low confidence the sample is going to be meaningful, to show that I have a very high failure rate or not, uh, sometimes it's not worth doing the test. If I can only prove that I've got a 60% confidence of a 40% survival rate, well, that doesn't really help me at all. I need to know if it's at some higher number, say 80, 90%, then I need more samples. So I use this equation with decision makers to say, well, where's the decision point, right? If this medical device is at 80% failures in 1 year, will you ship it or not? Was that a trigger for you to take a look at it? And if they say no, if it's at 20% failure in 1 year, that's too high. I need to know if it'll do 90% or better. So then I put in 0.9 and calculate the number of samples. And that becomes a cost. And they go, oh, I can't afford that. I says, well, you can't show that you're at some level of reliability with confidence for free. And you can see very quickly, it becomes a trade-off, right? So what's that information worth to you? And so as I vary R, I need higher, I need more samples. If I reduce the confidence, I need fewer samples. But careful, what happens if you reduce the confidence to 50% or less? What does that mean? I bet you didn't know you were going to get a statistics quiz here in the middle of this webinar. If I go below 50%, what does that mean? Yeah, low confidence, but it also means, let's say it's 50%. It means that the true value of the answer, saying this reliability number, let's say it's at 90% survive 1 year, it means that my sample is estimating where the true value is, but it's only half of the value, half of the time I run this test, it will bound or be close to the actual answer, and half the time it will not. So it's about like a coin flip, whether my test is meaningful or not. So going to low confidence, get below 50%, the test becomes pretty meaningless. So if I'm at a 10% confidence, I may only need a couple of samples, but the result will be likely different 90% of the time. So the test really has very little value at that point. So I tend to say, and you see this on data sheets all the time, is 60% confidence is kind of the accepted low value for type 1 confidence. I've seen others use 50%, but I look at that as the threshold to the test is meaningless. So be careful with that a little bit. So C, confidence, is that I think the classic definition is if I have a 90% confidence, it means that 9 times out of 10, when I draw a sample and run the test, that the result will be representative, relatively close to the actual value. So if I'm trying to estimate time to failure and I want to show that 90% survive, say, a year, or more survive for 90% or more survive for a year, if I have a 90% confidence, that means when I take those samples and run the test, that if I get an answer that says, yes, 90% will survive for a year, that the true answer is 9 times out of 10 is the same. But one time out of 10, we don't know which one, the true answer is less than 90%. So the actual true population might be at 80% reliable, but because we picked samples at random that were all good performers, all lasted well into the over the year, um, I my sample misrepresented the actual values. And so that's what the confidence is about, is can I trust my sample? And so if you want higher confidence, you can see very quickly it'll be a lot of samples. So M, Ray, is in the units of lifetimes. So if I'm interested in a 1 year period of time, then M is 1. If I only have the ability to test for half the lifetime, right, only simulate or accelerate it so that I get 6 months worth of life, then M is 0.5, but it doubles the number of samples I need. If I can run the test at a highly accelerated way and I can get out to 2 or 3 years of time, then M would be 2 or 3 respectively. And you can use fractions here. And so you might be able to run 1.5 lifetimes, and so it'd be 1.5. Um, but it's in units of lifetime. Okay, so we get this question on sample size all the time. So yet the biggest piece of this is what's the risk? What is this test going to tell me? If I run one sample, um, just run it to failure and learn something from what fails. If you've got 10 samples, well, how long does it take before the failure occurs? Or how much stress does it take before the failure occurs? And now I'm starting to talk about distributions and time to failure or stress to failure, but there's still risk. Those 10 samples might be the most robust ones and fail at on the high end of the strength curve. So what I'm after is that stress strength curve in many, many cases. And the risk is how accurately am I showing where that curve really exists. And so that's what I mean by risk here. Now, we get fewer and fewer options when we have limited samples. And I mentioned a couple of ideas here early on, but in general, it's if we're lucky and we can measure a decay in the performance, say a wearing or a slacking off of performance, a loss of power, for example, then we can use techniques that measure the system over and over again, and we get some better use of the very small sample sizes. Sometimes we just have to run it to failure. It's it's the best information we get is what fails. So things like highly accelerated life testing or discovery testing, find the margins is the best use for our limited samples. But if you're really interested in what's the lifetime of something, it really means focus on the failure mechanisms. What exactly is causing the failures, and how can I extract that information out of the very few samples I have? And it's a challenge we're all going to face if you haven't already. Uh, Dealing with very small samples, the best advice I can give you is focus on the failure mechanism. What exactly is causing the failures? And then for every sample, get as much information out of it as you can. Yeah. Yeah, you're exactly right, John. Some industries you get no samples at all. It's all simulations and modeling and you know back of the envelope or more sophisticated methods to calculate it and sort it out. But when it becomes critical, then you take out subsystems or coupons or surrogates or some way to look at the materials themselves directly or look at just the motors separate from the old system. And it's a variety of different ways of dealing with that. But we're all going to deal with it at one point or another. So kind of answered some of that stuff, and just a quick summary here. But I wanted to mention one other thing is I just launched a program called Dare to Know. It's Tim Rogers and I have been interviewing mostly reliability folks at the moment, but the reliability thought leaders. And I've got the 10th interview. I got to get it posted, but it's up on that Ascendo site. So these are 15 to 20 minute, I think one of them went to 25 minutes, interviews with book authors, bloggers. We've got some university professors teaching reliability programs coming up, but I'm hoping to make this a regular podcast series. So we've got 9 of them recorded and posted. We got another one in the queue, and we've got a whole slew of invites out so hopefully over the next couple of months we'll have some more interviews. So I wanted to mention that real quick. And then thank everybody for hanging out, asking some questions, and chiming in on the chat window. I looks like I ran a little bit over. Apologize for that. But I'll stay online to see if there's any questions and if there's any comments and stuff that we can address.